All right, well, good morning, everyone. My name is Lyle Tavernier, and I'm speaking with you from NASA's Jet Propulsion Laboratory here in Southern California. Excited to talk to you today about deep space and deep ocean exploration. In just a few minutes, we're going to actually hand off to a research vessel that's out in the ocean, where we'll be able to talk to a couple folks and find out what Brandon and Aaron are up to out on the ocean. Before we do that, we're going to just kick off a quick little demo. And this demo is a great way to talk about sea level rise and some of the causes of sea level rise. I'll put a link to this activity in the chat in just a minute. But what I want to draw your attention to is this little setup that I have over here. I've got two bins. This is our land ice and sea ice demo. And what we're going to do is we're going to put some ice on the land, which would sort of represent maybe the Greenland ice sheet or ice on Antarctica. And then we're going to put some ice in water, which would represent ice that would form in very cold water that then freezes out in the ocean, not on land. And so what we're going to do is we're going to do that, and then we're going to step away so the ice has time to melt. But before we do that, we're going to make some predictions about what we think, which situation or which case will be the greater cause of sea level rise in this particular instance. So I've got my setup already made here. And basically you just need some clay. Do not use Play-Doh because Play-Doh will dissolve in the water, but just any sort of clay other than Play-Doh. And from there, we're gonna just put some ice on the land here. And it's kind of hard to see because the water is clear and the tub is clear, but there's actually some water in here. You can kind of see it wiggling there. And I've marked the edge of the edge of the container so you can sort of see where it is. And I'm going to put about 3 or 4 ice cubes on here, depending on how many I can fit. I want to make sure that they're on the land. And in the chat, if you would, what I want you to do is just make a prediction about whether you think it's the land ice or the sea ice that's going to contribute more to sea level rise when it melts. Now for the sea ice, it's a little different. I actually put it into where the ocean will be. I spill ice all over my table. But what I want to do with this is actually need to pour water in so that the ice floats just off the ground. So once it's there we go. Once I've done that, I can put a little mark on the water level. Come back in a little bit and take a look and see where that water is at. So let me just come back to my screen here. And now I'm just going to pitch it over to Brandon and Aaron on the Nautilus. So Brandon and Aaron.
Hey guys, excited to join you. I have a vote as to which one will contribute more to sea level, but I'll keep it to myself. My name's Brandon. I'm joined here by Aaron out on the EV Nautilus. Really excited to be with you guys. The timing is just perfect. We've been out here for just over a week and are finally seeing conditions right to test a new autonomous surface mapping vehicle. And I want to show you guys a little bit about that and give you kind of a quick tour of the ship. Some of you guys are familiar with the Nautilus already. I know I've spoken to a lot of teachers about it because it's an incredible research vessel, not just because of the great footage that it takes of some just amazing undersea environments, but also because as an educator, they have an incredible program for teachers that actually sends them out to sea and get to dial into classrooms across the country, kind of bring all of this technology into different classrooms and set the stage for some really exciting lessons. So JPL and Nautilus have kind of been put together this workshop as a chance to kind of show you guys some really cool educator resources as we get back to school. Just kind of give you guys a quick look around the ship. Just outside, if you got here a couple minutes early, I was showing people this. So this is out the back. You can, on the back deck, you can see there is a crane that's holding a pretty large gray gondola. You can see people leaning over there for scale. And if you catch the wave right, in the back there is a orange kind of feature just above the water. And that is a small wave-piercing autonomous vehicle that is equipped with sonar and able to kind of map shallow waters. So the Nautilus itself are on it and maps far, far deeper. But what if we could potentially run two vehicles simultaneously, one in shallow water, one in deep, and be able to see and effectively collect that much more data. The view out the front, it looks like this, which is, effectively, flat water for 360 degrees most days, but you get really, really beautiful sunrises and sunsets, a nice way to enjoy your coffee, hazelnut or otherwise. But you kind of can't capture the beauty of the vessel that we're on right now, which kind of looks like this. So this is some drone footage taken earlier of the vessel as a whole. So you can see this is where we've been for the last week. We've got 2 more weeks aboard before we get back to Honolulu to port, and this is kind of where we spend our time. Really, really, again, an amazing ship. In the past, you might have seen footage of the ROVs. Then that's our subsurface exploration, where you get to see footage at the ocean floor. Some of my close network, you guys know that I had been out on the Nautilus in the past back in 2019, and this was an ROV expedition where we sailed from Johnston Atoll. I effectively flew into American Samoa and sailed to Honolulu from there. So again, covered a lot of ground and explored the ocean underneath, and just really some incredible findings of different coral species, squid, octopus, all of the really exciting stuff. That all gets brought up into a small wet lab shown here, which is just kind of a simple laboratory, mostly bag and tag, the kind of things that we would take back to research universities. But as of right now, the bulk of the work is being done here. So you can see these guys, we've got the engineers all on hand as we attempt this recollection of our vehicle that's been out in the water and deployed for the first time. So really just a super interesting cruise so far. Very different from what you guys might know as the the kind of ROV type expeditions that get you that footage that we all know, and this time instead really focusing on mapping, which brings us to our wonderful guest Erin, who I'm going to introduce here, and she's going to tell us a little bit about the data collection, the tools that we use, and how mapping guides the research that we're doing. So Erin, take it away.
Hi, yeah, so my name is Erin Heffron. I'm the mapping coordinator on this expedition. My background is in sonar and mapping, so that's very fitting. And for most, for the last week, we've been mapping with the Nautilus. So using the hull-mounted sonar, the EM302, to map deep waters. Our acoustic system is really set up to map much deeper than 200 meters. So just as a quick visual of what that looks like, can we switch over to this screen? And this is just kind of your standard image of multi-beaming. That's what we're doing. So the picture Nautilus on the top, we send out an acoustic pulse of many individual beams, if you can imagine that. That acoustic pulse goes down to the seafloor, it returns to the ship, and we know from the time it took to do that, how deep the seafloor is. We could put all of that information together to make a nice map of the seafloor. And that's what's kind of being displayed here, the yellow being the visualization of the acoustic pulse, and then it painting the seafloor behind it. And so we've been doing that on Nautilus for now a week. We can do that as well with Drix. So if you could picture this little reddish orange vehicle at the top with a different sonar, they will do exactly the same thing, but in shallower water, because they have a different sonar that's more keyed in for that depth of water. So if I just swap out my screen, so I'm going to kind of describe what a mapping workflow looks like. That was the cartoon. Now I just want to show what it looks like in real life. So when we are acquiring data, our sonar is at 30 kilohertz, which is a medium low frequency. That lets us get down to some of the deeper parts of the ocean. So and you can see in this screenshot, we were acquiring data in about 4,500 meters of water, which is pretty deep. It's fairly deep. And this is what it looks like on our end. We're running the sonar In this top display, we're getting a map view of the seafloor bathymetry that we're collecting. And in this bottom display, we're also seeing what's happening in the water column. So not only do we collect data on the seafloor, we can collect data from the ship down to the seafloor, and that is used for different purposes. We use the seafloor data for bathymetry, and we can also get intensity information to tell us a little bit about the seafloor. But in the water column, there can also be interesting things. And in this screenshot, you see near the top of the triangle, some bright colors. That's what's called the deep scattering layer. So you might have heard about that. One of the biggest migrations, or the biggest migration daily, as these little biology, these critters move up and down in the water column to go feed and then to go hide from predators. So that shows up as a bright, intense scattering in the acoustics, which we can see there. Other things we sometimes see in the water column are things like gas seeps. Bubbles really reflect acoustic energy. So when we talk about mapping, we are mapping most generically the seafloor, but we can be mapping all these other things too. We can be mapping scattering layer distribution. We could be mapping location of seeps. We could be mapping biology. We can do quite a lot with acoustics that most people don't know is another option, I guess. So just continuing on. I have a second shot here. This is just kind of zooming in. So I think it's important to, I don't know, I've set this up to describe what the workflow looks like for us, and then you guys kind of see the end products. That picture I showed you before kind of showed like a continuous surface of the seafloor, but this is kind of a zoom in on the same thing. And it's just, I want you to key into the fact that though it looks like this nice continuous surface that we're actually collecting all these individual measurements, I guess you can say, with the acoustics. So each of these is a sounding or one measurement on the seafloor from this multi-beam sonar system. And the space between them is the time it takes for the one pulse to go down and return, and then for another pulse to go down. So you'll get a bit of a gap in between as the ship keeps moving forward. And then from that, we start to build up what our data set looks like. I think I'll just step back just shortly, just to talk about why we map. We are almost always mapping on Nautilus unless we have the ROVs in the water. And the reason is, especially out here in the Pacific, the reason being that most of our seafloor has not been mapped. So this is a really nice visualization of the Pacific. It might be a bit noisy, but you see the continental US there. You see Hawaii right here. And everything that is not colored, everything that's black, is not been mapped by multi-beam sonar. So if I then zoom in on where we are, so really focused on the Northwest Hawaiian Islands. And we are right in around here. Well, right now we're right here, actually. So that's been pretty well mapped. But as you move over here, all these big black gaps, that's what we are always working to try and fill in, to try and complete this picture of seafloor mapping. And then, so we collect the data, we do some planning, and then we start to get some really nice, I guess we call products. So the first thing I wanted to show you is what the data looks like to us when we get it. This is what we start with. So we start with just a bunch of points, millions and millions of points. And from that, we have to make sure it looks like seafloor, make sure there's no issues with it. Then we'll start to get around to building more models of the seafloor. So this is what the data looks like to us when we're exploring it. And this is a seamount that we mapped. We finished mapping a day or two ago, but this took multiple days to go back and forth. Not just over this feature, we were going about 100 nautical miles on each pass. But this is what it looks like in reality. Like each of these little tiny dots is a measurement or a sounding on the seafloor. And this is what it looks like at the initial stages as we're cleaning it and processing it. And you can just see the really cool detail that we get with the sonar. Then after we clean it and start to get it together, this is probably more the view that you might be used to seeing. And this is a perspective of a digital elevation model. So we take all those points and we make them into a surface. And then that gives you a better kind of feel for what the seafloor looks like. When we're working with our data, we use a lot of different software that's really specialized. This is one called Fledermaus that gives us these really nice 3D views. And what I wanted to show you here is that when we make these elevation models in our specialized software, we can just move our mouse around and we can visually see that this is higher than this, right? But we can also get depth information. So I'm just focusing in on this corner, and where my mouse is, it was 2,152-ish meters. But that's not always easy to convey to other people. You can also see it in the color map here. By looking at the color of the digital elevation model and looking over here, you can guess what the seafloor depth is. But you as a viewer don't have the control of the mouse, so you really can't get a good feel for that information. So another way that we convey mapping information, which you might be more familiar with, is with contours. So I also have the same thing with a contour map. And this is the top-down view, looking down at the same feature, and I've used an algorithm to generate contours. So a contour being a continuous depth. So these white lines are all following the same depth, and I'm showing you where the 4,300 meter contour is, and then that tippy top contour is at 2,100 meters. So this is just another way to visualize seafloor data. And this is kind of what more people might be used to if they're used to looking at seafloor or any kind of topography at all, using these kind of simplified ways to look at the data, like a contour map. And I have that one in 3D as well, if I can bring that up. So that's what it looks like if we're looking at it from a different perspective. Our map looks like. And so as mappers, we don't think about contours that much because we have so much control over the data. But for getting across ideas to people, sometimes contours are more powerful and help people have a better idea of what you're talking about these changes of depth. And then kind of one more thing I wanted to mention. I know you guys are thinking sometimes about vertical exaggeration. We vertically exaggerate our data to make it look more interesting, I guess you can say. So this is this image I'm bringing up. This is real life. So this is the seamount that we were just looking at, unexaggerated. So is what it is. It's still pretty cool, but it's maybe not as powerful as you were looking or hoping to convey. So as mappers, we often vertically exaggerate things for interactions and things like this. So if that's 1 times vertical exaggeration, I can bring up 2 times, which is what I've been using on this cruise, because it conveys that this is a pretty cool thing without being over the top. But the default vertical resolution or vertical exaggeration is 6 in a lot of our software. And so you can see that you can very easily kind of go over the top with vertical exaggeration and kind of lose the effect. So hopefully that helps visualize what vertical exaggeration looks like with this kind of data that we're working with. And then just one last thing, another thing that we often do with our data is do slope. So we can calculate the slope over the area. This is something we often do when we're preparing for ROV dives. So here I took that seamount, and instead of coloring by depth, I've colored by the amount of slope. And anything that's over, I believe if I set my threshold at maybe 25, anything over 25 degree slope is this really bright red. So using the visual of the color map and the visual of this 3D model, I can convey areas that we wouldn't want to necessarily land the ROV on, or that we might want to approach cautiously. And it just really helps focus your attention using both the color and the terrain models like this to get across the data that we're collecting. So how was that? Was that a good description?
Yeah, that's awesome. I hadn't seen that slope before. And how that guides part of
Hey, Brandon, we're having a hard time hearing you. Your audio is not coming through.
I might still be on mute. Yep, there we go.
Much better.
Yeah. This really cool. I was just saying that the slope data in particular, I think is really interesting. And again, thinking of the ROV dives that have made the Nautilus so popular, how and where we go and explore, right, has to start with mapping first. We got a couple questions in the chat. I invite you guys to throw in some more, and we'll kind of get a few questions out to Aaron here. The first one that Lorraine asked is, when the mapping is done, how does the data get sent? Who does it get sent to? And how long does it take before people can really work with the data?
Oh, that's a really good question. So while we're on ship, we only send things ashore for production purposes and things like that in the kind of the brief time while we're actually at sea. But then as soon as we get to port, we have processed all this data, we've packaged it up, we have it ready to go. hard drive goes to University of Rhode Island, and it's available there pretty quickly. I would say within a week or two, because somebody physically hand carries it back, all the data. After that, it just goes through a process. We go through the University of Columbia La Montardi, and they help to get it exactly how they want it to go into the National Archives. And as part of our agreements with NOAA and other organizations, that data must be publicly available. It's either in 30 or 60 days. So we get it up there as quickly as possible. But within a week or two, if this data was of interest to a particular party, including any of you out there, you could do a data request. You can request it earlier than that. Just probably within a week of the cruise, it would be available. Just takes a little bit longer to get it to the archive and for the archive to upload it and make it available on some of the websites that you might be more familiar with for getting this kind of data.
Cool. And Robert's asking, what's the resolution on this map? And can you kind of talk about, obviously this has been kind of smoothed and you showed some of the sounding points, but.
Yeah, so when we look at this terrain model that I was showing, and yeah, you can bring up the slope map and I can bring up some other ones too. Each square, so you can actually see the little squares there along the edges. Each of those is 75 meters. When we are thinking about what resolution to display our data, we usually estimate somewhere between 1% and 5% of water depth is a good resolution to make these surface models out of. So 75 meters and 4,000 meters of water is not bad. That's pretty good ability. And so we also have to make kind of make decisions about it. So, okay, we could try making a model at 1% of water depth. So let's say 40 meter cell size, but we might start to have a lot of gaps in our data. And I could just go back briefly to that image of acquisition. Give me one moment. So just looking at how the data comes in when we acquire it, we often have really nice data density in what we call the across track, right? So we have many, many points across there, but based on the speed of the ship, we may not have the same resolution along track. So if we make too small of a cell size, the model will start to have a lot of holes in it. You could picture there just being no information here, but there's quite a bit of information here. So we pick a resolution or a cell size to display this data that is appropriate for the data. And you can also do a little bit of math with it. It's all just based on simple trig. We have a 1 degree system. So what does 1 degree look like on the seafloor? You can calculate that out. And when you populate 1 degree to the seafloor, let's just say it ends up with a 50 meter, 100 meter footprint at 4,000 meters. I didn't do the math, but then that is an appropriate resolution for the system. As we get shallower, that cell size is going to get much smaller. So when we're collecting data with the DRIX and it's high frequency resolution sonar and it's probably has a smaller degree, I'm not sure what the degree of that one is, we're going to have things like 1 meter cell size to maybe 25 meters. So it varies hugely over the depth of water. But for 4,000 meters of water, 75 meters is pretty good. Hopefully that answers that.
Yeah, one last question I was wondering about too is you mentioned, right, that this is all acoustic, but what does calibration look like since sound is going to travel at different speeds as it moves through the ocean?
Right. Yeah. So sound speed is really important part of our mapping, right? When we are collecting acoustic data, we take sound speed profiles. So if you ever tune in to Nautilus Live during a mapping cruise, you might see us out on the back deck, and we are dropping what's called an underway CTD, so underway conductivity, temperature, and depth. And we drop that probe. It can only get to about 500 meters, but that gets us through probably the most change in the water column. As you get beyond that, the water column is pretty static. There's not a lot of change, and so sound speed doesn't change a lot. Sound speed changes with temperature and salinity. So as you kind of get past that part where it's changing a lot because of the water temperature, it's going to change less. So we use those sound speed profiles that we collect. They get pumped right into the multi-beam and are actively applied by the sonar in the background. So the sonar is doing a lot of really complicated math to come up with where actually that detection was and actually how deep it is. We're also monitoring sound speed right at the system head. So we have a constant running sound speed to know, and that's more for the intrinsic internal parts of the sonar for it knowing where its beams are going and where they're coming from. But yeah, it's a really good question. If you don't apply sound speed, it would assume probably a generic like 1500 meters per second, and you'll start to see artifacts in the data. And so we are always keeping an eye out for that. If we start to see this nice flat seafloor surrounding that seamount, if it starts to turn up on the edges, we know that's not real, and we know that we're having a sound speed issue.
One last question for you before I let you get breakfast.
Yeah.
Are there types of features that are unique to the ocean floor that we don't see on land?
Well, I mean, I guess so, yeah. But there's probably similarities to things on land. I'm like, my mind goes to, you know, they may not be, because like I think about spreading centers, but we even have rift valleys on the continent, right? So where the seafloor is pulling apart and we have active basalt coming up, well, there's active rift valleys in Africa where the land's pulling apart. We have hydrothermal vents on the seafloor. We have similar kinds of features on land, maybe not exactly the same, but we'll have different kind of sea piping environments like that. So there's probably a few things that are very specific to the seafloor, but mostly, I mean, it's similar topography to what we're seeing on land. A lot more deposition because it's underwater, and whereas the land is an erosional environment, so that's going to draw, that's going to change the shape of the earth because it's all about erosion. As we get into the ocean, it's all about deposition. It's no longer eroding, so you'll get deeper sediment basins and things like that. But there is a lot of similarity. It's just harder to see.
Beautiful. Well, thank you so much for joining us. I really appreciate it. Hopefully everyone found that informative on again how important mapping is as our kind of first pass, terrible pun intended, for seafloor exploration. So Lyle, back to you.
Awesome. Thank you so much, Aaron. I know I actually just learned a ton, and I've got some new ideas for some lesson modifications. But I want to talk about some lessons, in fact. And one of the things that I want to talk about, as I mentioned earlier, there's a lot of similarities between deep sea and deep space exploration, including things like extreme pressure or lack of pressure in the case of the ocean, or excuse me, in the case of space exploration. But also the way that we map surfaces on planetary bodies is very similar to the way that Aaron described mapping the ocean floor. And so a lesson that we have out now, it's maybe just a week old, and I'll put the link in the chat here in just a moment, is all about mapping planetary surfaces. So there's the link for it, but I'm going to put it up on the screen so you can take a look at it. And effectively, what we're doing is we're taking the same idea that Aaron described in space, but instead of using sound waves, spacecraft will use radar or LiDAR. So just a different kind of signal, but the same concept in terms of sending a signal down, timing how long it takes to return, and figuring out how far the signal actually went before it bounced back. And so what that does is it gives us, as you saw in Aaron's imagery, these different swaths of planetary surfaces. And if you've got a spacecraft that's orbiting around a moon or an asteroid or a planet, you can get full coverage of that map or of that surface. Whereas if you've got, let's say for example, the Cassini mission, which was orbiting Saturn, would occasionally fly by Titan. And as it would fly by, it would measure a swath of the surface of Titan. And so you get these different swaths crisscrossing, and you could kind of see some of that in the imagery that Aaron was showing. That eventually you can piece together a more complete picture. Now, we've got an upcoming mission, the Europa Clipper mission, that will be launching in a few years to, it won't actually be orbiting the moon of Europa. It will be orbiting Jupiter, and it will pass by Europa probably about 50 or so times. And it's designed in a way to capture the most surface area as it does that. So it'll be sending radar signals down and mapping those different surface features. And again, more with these similarities, as Aaron had mentioned, sort of taking into account the medium of the water that these signals are passing through from the boat. Radar can actually pass through different surface materials, so we can even get a sense of what sorts of features and structures are below the very top surface, and maybe look below and see, are there bodies of water within the ice shell of Europa. So these are the kinds of things that we can do. And I'll put it up on the screen here. If you're not familiar with our lessons and activities, you'll see a pretty simple material list here. In this case, really all you need are some colored pencils and these worksheets that we provide for you. But effectively, you get a little background on how we use radar mapping throughout the solar system. Here are some of those swaths I mentioned on Titan that we can collect and get a better picture of what the surface looks like. Even if we're not completely mapping the surface, we can still get a much better understanding. Now, what the students are provided with is they're provided with simulated data. And what you as a class or what the group would do is decide, okay, when I have this data point that I recognize is 100 meters above the surface or 200 meters, what color are we going to do that? And from there, students will actually map the data in, and then they have to figure out what sort of feature this is. Let me see if I can zoom out so you can kind of get a better look at what a swath might look like. So they'll take a look at these. That actually scrolls very weirdly. Let me just see if I can zoom out a little bit more and get a larger picture of the swath. So effectively, there are about 5 or 6 of these different swaths, and the students in the groups will try to map these things out. And there are different ways you can do it. You can just color right on these sheets. But you can also, if you've got students who are trying to learn or familiar with conditional formatting in Excel, they can do that. And effectively, what you would get is a map like this. And you can see, similar to what Aaron was showing, we've got colors representing different heights and showing what different features might look like. And so you've got all sorts of different features that you can find in these activities based on this simulated data. Now, what's fun about this one is once the students are done creating that map, you can have them create a physical model of their, this is kind of hard to see, I'm going to hold it up close here. They can create a physical model of what they've been working on. And I made this one out of Legos, but it can kind of be whatever you actually want. I'm going to ask Brandon to share his model that he made with this lesson. But it also addresses that aspect of vertical exaggeration that Aaron was talking about. So there's a component to this lesson where students have to calculate, well, they don't have to, this is an extension if your students are capable of it, of working out the vertical exaggeration of this, because this is very, very, very exaggerated compared to what the data show on the map. So kind of a neat way to get students thinking about how do we look at surface features, how do we understand what sorts of features are on these planetary bodies, and not just planetary bodies, but our planet itself. So kind of a fun one there. Brandon, do you want to show your model that you created? I don't know if you did what feature you did, so actually I'm just going to ask you to show us.
Yeah, I don't want to show you because mine was pretty bad, and I want to blame a couple things on the ship. But I tried to make a similar model as Lyle's, but as a C mount. So I tried to make mine subsurface. So effectively, my axis and the Y gets larger and larger as we go down. But I did not heed Aaron's lesson on vertical exaggeration. So I made my scale bar first, and then tried to make it with Play-Doh after. And oh boy, I needed a lot more Play-Doh. So you can see here, I've kind of got an axis in the back. I've got an X axis on the top, just so that you could see it. But I was out of Play-Doh pretty quick before I even got anywhere near the top. So I probably should have upped my exaggeration instead of going 1 for 1. Play-Doh it was not as great for me. I felt like I was using a lot of material. So the Lego, especially, an off-brand Lego, you can get a box of 1,000 for like $15. So that at least gives you some reusability. But I kind of like the idea of trying this. I'll kind of break this down real quick, using kind of like a backboard as an idea to kind of set an axis that could be plotted against.
Yeah, I like that background too. And I'll make a comment too in terms of Brandon using a lot of Play-Doh. This is kind of why we try these things out to see how they work before we send them off to you. I did this so color-coded for a photograph. I do not encourage you to ask your kids to do it like this because the most important part is really the profile here. What's high, what's low. It took a long time to find all the right colors at just the right height. So I wouldn't worry so much about the color if they're doing a physical model. I'd be more concerned about trying to get the model to match the simulated data that we have provided for them. That's kind of my little, this was something I found out doing this activity. So yeah, kind of a fun one. Let's see. So let me look at our agenda here. We've got about a little less than 10 minutes. So real quickly, what I want to do is let me just, I'm going to give the land ice, sea ice just a few more minutes because it's not as warm in here as I thought. So the ice isn't quite melting as much as I thought. But as the chats were coming in, I was seeing about a 50-50 split for land ice versus sea ice, which is actually kind of typical for what we get. And then nobody gave me any explanation other than just because they saw that I had gotten a few votes for one versus the other, and so they picked the other one just to be contrary, which, you know, that's a great reason too. So while we're doing that, if you're not familiar with our website, what I want to do is just kind of give you a quick tour. I'm not going to go into details about all the different features that we have here. But if you go to our website, and I'll put it in the chat, jpl.nasa.gov/edu. This is what you'll find, and you'll see a few headers up at the top. You'll see interns. So if you've got maybe high school seniors who are going into college for science and engineering or math, that's a place they might want to check out their freshman year to see about different internship opportunities that we have here at JPL. Our Learn section is really student and at-home learning focused. So a lot of DIY projects that students can take and do on their own. We try to get them away from the screen for a lot of these. So it'll give you step-by-step directions, and then they just sort of go on with what they're going to do. Events, you may have found out about this event through our events page. We've got it on here. You'll notice you're pretty fortunate because we filled up pretty quick. But you can see other events, not just workshops, but things that are going on around NASA that may be interesting just to check out for you or for your students. And then we've got the news section. This has a lot of intern profiles, but it also has what we call our teachable moments. So if there's something cool happening in the news that students are hearing about and you want to know a little bit more about it too, so you can talk to your kids about it and even incorporate some activities into your teaching, those teachable moments are a great way to find it. And then the teach section is sort of the real, I don't want to say guts or the meat, but the bread and butter, I guess, if we're going with sort of food and digestion. This is where you'll find all of our different activities, all different types of activities, different subjects, grade levels, topics. And I'll just sort of go to this one that we just talked about, the Mapping Alien Worlds, just to give you a sense of what you get. You get the details in terms of grade level appropriateness. This is our estimation based on the standards that this is aligned to. So if you look at this and you're like, you know, I teach third graders who would absolutely love this. You know, there's no reason that you can't do that and adapt it for your students. Gives you some of the standards that are addressed by this, materials management, so tips that we think would be helpful for you running this in the class if you haven't done it before. A little background information beyond just, you know, here's the activity, here's what you do. It's really like, why does this activity matter to scientists and engineers? How are students going to connect this to real life? And then we go through the procedures, just step by step. Here's what needs to be done. Here's how we do it. And then we've got some discussion and extension pieces. And these are all of our lessons have these different components in here. So if you go into the teach section and scroll through, you'll see lots and lots of different activities, all with that same sort of background and materials and things like that. And in terms of materials, Brandon and I, we were former teachers. The other folks in our group, we were all former teachers. So we're not trying to give you a lesson plan that requires you to buy $3,500 units of something or other. You know, a lot of these things are like off-brand Legos and Play-Doh and, you know, sticks and straws and whatever else is super affordable. So let's see. We've got some more votes coming in for land ice and sea ice. Okay, all right, so we're doing good here. What I want to do is just check out our land ice and sea ice. And I gotta say, it did not melt as much as I thought, but I think it's still noticeable. So if you look over here on the right-hand side, nope, that's the left-hand side. If you look over here on the left-hand side, you can see my mark here. Almost all of the ice is gone, and that mark is still where the water was when we started. Now over here, almost none of the ice has melted, but if you look really closely, I don't know if I can zoom it in here. I'm gonna try, probably will not zoom in right where I want it to go. You can kind of see on the very edge of the screen here, the water has actually gone up just a tiny bit, maybe like a millimeter above that line from the ice on land. Now I got a couple different responses in the chat. One of them had thought, well, you know, the The clay might absorb some of the water, which absolutely true. Clay definitely has some moisture in it, but it's pretty saturated. It's not going to absorb a ton. And so this is where it gets kind of interesting, is which one causes sea level rise, or contributes to sea level rise, I should say. It's the land ice. It's the ice that is on land that's then melting, and that water is being added to the volume of the ocean. So whether it melts in Greenland and runs right off, or whether it melts in a glacier and goes through a tributary system down to a river that empties out into the ocean, it's that land ice that's melting. The sea ice doesn't change significantly, and that's because the volume of the ice is replaced by the volume of the melted water when it melts. So you're not going to see a change in sea level rise based on ice that formed in the ocean then melting. So just kind of a neat one to think about, and a connection you can make to the students if they're doing this is, what happens when you've got a cup full of ice on a hot day? It's not going to overflow when that ice melts. It's going to stay right in the cup that it's in because it's not contributing. Versus if you've got, a plate of ice that's pouring down into a cup, it's going to overflow that cup eventually. So kind of a little real life connection there. So what I want to do is just take a look. Let's see, we need to have Brandon tell us a little bit more about his website over there on the Nautilus. So Brandon, if you want to take that.
Sure. The sea ice, land ice activity is also on the JPL education site too. So even things that are like shorter demos will be available as well. And same thing with a little bit of background. I'll say too, since there's some new people in here, if you guys haven't used the website, especially if you're like an early career teacher, having all of those lesson plans, the student worksheets are already made. The answer keys are already made. You got to be careful about that because my students figured that out pretty quickly. All these activities are already like done for you. So like, I think one of the things that Lyle and I really try to do is to make sure that, your jobs are made easier, right? That you don't have to kind of start from scratch, or this should just be something you guys can pull right off the shelf. The Nautilus Live site has an education website as well. I'm going to show you guys that really quickly. So it's at nautiluslive.org/education. And you can see here, much like Lyle walked through, there are some education activities here that are broken down into categories and are lesson planned as well. Also NGSS aligned, so standards aligned activities, as well as just like, graphics and videos, some things that maybe would just be great engagement material. But you might also see that you guys have opportunities to request a connection, kind of like how we are doing right now. If you want to have someone like myself talk live from the ship to your classroom as the school year begins, that's the link that you would click, and you can kind of send some suggested times, and someone back on shore will schedule with you. So that's always just a really great opportunity, especially if a dive is going and they can kind of see live footage from the vessel. And then lastly, if you teach older students, or you have children of your own that are of kind of finishing high school, early career, college, that kind of stuff, there's an internship site as well. So we actually have quite a few interns on board here, mapping interns, engineering interns working on the devices. And as I mentioned at the very top, also right? Teachers can come out and do this. So I encourage you to apply. It's a super, super fun program. You don't have to be out for 3 weeks like I am. I think the expeditions are as short as 7-8 days. So it's really, really an incredible experience, a chance to really be part of the science out here. So I encourage you guys to apply.
Sorry, I had to unmute myself. Thanks, Brandon. So if you've got any questions, throw them into the chat. Otherwise, we are getting ready to sign out for the day. Thanks so much for taking some time out of your Saturday, especially during your summers. So really appreciate you taking the time for that. Means a lot to us. And just a note, as I mentioned when we were hearing from Aaron, I got some ideas about how I could maybe change some of these lessons. In fact, how I can adjust that brand new lesson that we just posted about mapping planetary surfaces. if you do a lesson and you think, hey, it would be really cool if you know, this was part of it, or here's what I did in my classroom, let us know. We're happy. In fact, we really encourage that because these are ways that we can improve the lessons and activities and make them better for you and for your students. And so if you've got those ideas, in fact, somebody in the session right now sent us a suggestion and we incorporated it into one of our activities. So it's absolutely something that we benefit from as well, and then others can benefit as well. So looking at the chat, I don't see any other questions. Oh, maybe if I scroll a little bit more, there we go. All right. Looks like no more questions.
I got a couple just
Okay.
really quick for you. Someone had asked if there's financial assistance or fellowships if they go out to Nautilus. Obviously, the Nautilus covers all the costs, and if it is during the school year, they'll even offer financial assistance if you need a sub and stuff like that. So yeah, it's everything's covered. They port in and out of Honolulu, so you could do worse. Yeah, it's but obviously no cost to you guys or the school. And then there was one more. When is the next Saturday training session? Soon. Lyle and I need to actually sit down and calendar these out. If you are in the LA area, we will be returning to in-person soon as well, but we'll make sure to still have the online offering periodic.
All right, sounds like Brandon, we froze up. You'll be offering online periodically, and then I didn't hear what you said after that, but hopefully everybody.
Oh, caught. Sorry. Yeah, we want to make sure we still have access for you guys abroad as well, but really excited about in person too.
Yeah. That was another question I had when the next ones are. We're working out our schedule for the coming school year. And then one other question, last one. Is there mapping software that you would recommend? And I would kind of, you know, I'll give my answer and let Brandon answer as well. I think ArcGIS is a pretty good software tool for mapping. It can take a little bit to get over that initial, like, what am I doing with ArcGIS? But there's a lot of online tutorials. It's free for teachers, so you can check it out and just do some pretty amazing stuff. We have some activities on our website that use ArcGIS or something similar to ArcGIS for like mapping features on Mars and things like that. But Brandon, I'll pass to you if you've got a different answer on top of that.
Yeah, you definitely stole mine. I like ArcGIS the best, and I mean, obviously it's a little bit more user friendly for older students, but it is also a career builder. And in fact, many of the interns who are here in the mapping world are very familiar with ArcGIS. That's the kind of thing that really opens doors for jobs. It's, I mean, tantamount to you know, learning how to code these days. So a very cool skill to have.
All right, well, that is all of the questions that I've got on this end. So I just want to say thanks again to everyone for joining us today. Really appreciate it. And Brandon, thanks so much for connecting in from the boat. And we'll hope to see you all again soon. Bye-bye.
Take care, everyone. Thanks so much.